Welcome to Calculus. Today we will investigate differentiating inverse trigonometric functions. We'll take a look at three examples, starting with this inverse of sine function. So our function here is y equals the inverse of sine of 3x cubed. So what we need really is a formula that will allow us to take the derivative of the inverse of sine. So I've got our chart here, and notice I've got all 6 inverse trigonometric relations listed. So we'll start with the first one, since that's the one we need. If I'm taking the derivative of y equals inverse sine of x, that's going to be according to this formula. So we're not deriving here, but if I would derive it, I would get the derivative is 1 over the square root of 1 minus x squared. So if I just had the inverse of sine, that would in fact be my derivative. But notice I've got a composition of functions where I've got x in my rule. Here in my actual function, I have the composed function 3x cubed. So what that tells me is I need to utilize the chain rule in order to take this derivative. So I'm going to set that up. So we're going to just say that y is going to be equal to the inverse sine of u. So I'm making a substitution there, and I'm going to say that u equals this composed function 3x cubed. So if I'm taking the derivative of y, using the definition of the chain rule, that's dy du, so the derivative of y with respect to u times the derivative of u with respect to x. So that's kind of my setup. Let me take derivatives of those two parts. So just based on the rule that I just wrote, the derivative of y with respect to u, so y again is the inverse sine of u, that's going to be 1 over the square root of 1 minus u squared, since I've replaced my domain value with u there. And then that's multiplied times the derivative of u with respect to x. So as I look up here, I defined u as 3x cubed, so the derivative of that is going to be 3 times the old power of 3 as a coefficient, x to the power of 3 less 1. So there's two things for me to do to finalize this. I do need to simplify that derivative of u that I just found. I also need to substitute back in 3x cubed where I see u here in my derivative. So those two changes. I'm also going to put that derivative of u in the numerator, multiplied times 1. So that's going to be 9x squared over the square root of 1 minus, and then I had defined u as that composed function 3x cubed, and that's going to be squared. So my final version of this derivative of y is going to be 9x squared over the square root of 1 minus, when I square 3x cubed, that's going to be 9x to the power of 6. And that completes the derivative there of that inverse sine function. So we won't use it here, but I do want to offer the rule for finding the derivative of the inverse cosine function. And like we see with derivatives of the original functions, there's a relationship between the sine and the cosine. Probably even stronger relationship here with inverse sine, inverse cosine. The only difference is that the derivative of inverse cosine is negative 1 over square root 1 minus x squared. Well, let's take a look at a second example. So again, I won't look at an inverse cosine, but let's look at an inverse tangent function. So here we've got the f of x equals the inverse tangent of 3x cubed. So it's really the same composed function, but now within tangent. So what we need definitely is an equation for the inverse tangent derivative. So we'll write that right here. Its derivative is going to be given by 1 over 1 plus x squared. So again, let's find the derivative of f of x here. So I'm looking for the derivative of f of x. And in fact, let me not get ahead of myself. Let me call f at u here the inverse tangent of u. And u itself we're going to define as that composed function 3x cubed. So really the same type setup that we used for chain rule in our first example. So the derivative of f with respect to u is going to be here with my Leibniz notation dy du times du dx. And to simplify life, I'm actually going to take away the prime notation and let's just call that y prime. And we'll also go back here, I think just to simplify our life, we'll substitute y for f of x. So that's set up for us to take the derivative. So I need to find the derivative of y with respect to u. So that's that rule that we just wrote. So that's going to be 1 over 1 plus u squared. And then I'm going to multiply that times the derivative of u with respect to x. So we saw that before. It's the coefficient 3 times the old power 3 as a coefficient, x to the power of 3 less 1. So then again, I need to apply the same two changes as I finalize this. I need to simplify that derivative of u with respect to x and multiply times 1. So that'll be 9x squared in numerator over 1 plus, and then I need to substitute back in my u function. Again, that's 3x cubed squared, and that'll give me this derivative, 9x squared over 1 plus 9x to the power of 6. So again, I've given the inverse tangent derivative equation. Let's also give inverse cotangent. So as you'd expect from that pattern between inverse sine, inverse cosine, there's a strong relationship between inverse tangent, inverse cotangent. And again, it's all about the negative. That derivative is negative 1 over 1 plus x squared. Let's take a look at a third and final example involving inverse secant. Inverse secant. So again, I've got the inverse secant function here, inverse secant of negative 5x to the power of 4. So that is definitely a composed function. Let's give our formula for the derivative. So the derivative of inverse secant of x is 1 over x times the square root of x squared minus 1. So just like we've done in our previous two examples, since I need to use chain rule, I'm going to define the function as y equals inverse secant of u. And u will call that composed function negative 5x to the power of 4. So then if I'm looking for the derivative of y, according to the chain rule, that's dy du times du dx. And let's take derivative of those two parts then. So the derivative of y with respect to u, that's derivative of inverse secant. So that's 1 over u times the square root of u squared minus 1 times the derivative of u with respect to x. So that's negative 5 times 4, the old power, x to the power of 4 less 1. So as I finalize this answer, again, I need to make those same two adjustments. In my numerator, I'm going to have negative 20 x to the power of 3. And then for this denominator, I've got actually two places where I've got to put the definition of u, negative 5x to the power of 4. So it does feature as a factor outside of the radical, substituting in there for u, and then the square root of negative 5x to the power of 4 squared minus 1. So my final version here is going to be negative 20x to the power of 3 over negative 5x to the power of 4 times the square root of 25, so that becomes positive with the squaring, x to the power of 8 minus 1. And that completes that derivative of this inverse secant function. Just to wrap up at the end here, we should put our final rule for the inverse cosecant function. And as you guessed, it's all the same except there's a negative. So negative 1 over x times the square root of x squared minus 1. Thanks for joining for this investigation of taking the derivatives of inverse trigonometric functions. I'll see you soon.